It is very easy to write the part of simplex table. So while solving an exam, is it necessary for us to write the problem table, or we can directly start with the simplex table? Because for finding simplex table, we just need to add the rows and then subtract. So
Uh, if I have not given enough time, if you are really, I mean, running late on time or something, that is fine. Otherwise, it is better you write the, I mean, problem table first, so that you understand it clearly. If you want to skip that step, uh, that is also fine with me. It actually depends on how much of mark. If I have just given 1 mark or 2 mark, you really do not have to write too much. I am actually expecting just very specific answer. But if I have given you more marks, then possibly I want you to, I mean, write things. So
okay,
depends on how. Yeah, depends on. Normally it is okay. You can directly write that, okay, this is the simplex table for the, I mean, the for page 1 to find the basic, I mean, basic variables, na?
yes, sir.
So you say like this is the new problem. We are minimizing y1 to, I mean, y1 plus ym subject to this is the problem. Okay, so now simplex table, simplex table, simplex table. You can write that way.
Okay, sir. Thank you, sir.
Uh, and like in the exams, as you have seen, I mean, I will be asking direct questions only. I mean, questions the way I asked in here also. Okay, this is the situation. What will be this? What will be this? What will be this? So if you have understood, you will not have any problem at all. But if you have not understood, then it will take some time. And then there will be some questions straight from the exercise. As you saw, there were 2 questions straight from exercise. And then there will be some questions which are new and which require some imagination. So 3 types of questions. One, testing your understanding. There will be enough questions for that. Then some questions from straight from exercise. If anybody has spent some amount of time in solving those exercises, I respect that, and I agree to give credit to that. And then there will be something new. So that is just to test your like this thing. Anyway, so shall I start now? Okay, then we were talking about this dual simplex method, huh? Uh, like last time I explained why. So I have written a little better way to, I mean, specifically answering questions. Why? Because this is another fundamental uh, style procedure to solve. And why? Because it is required in theoretical discussions. For example, it will be used just in this lecture, in the latter half of the lecture, in what is called the I forgot that. Okay, we will see. It will be, I mean, some when there is some perturbations, sensitivity analysis, right, that is the name of it, I forget. And that sensitivity analysis thing is some like old this thing. Nowadays nobody really gives it too much of value. I mean, unless you are pursuing optimization as some research or some, then further some further course or something. Anyway, it is better to know what is it. So geometrically I have told that what it means. It means starting from a corner like point from outside, where the affine cone at that corner point contains the whole of t, and the objective function is minimized at that corner point. So that is from where you are starting, and then you are writing the doing the dual simplex step. Okay, so for example, if we are starting at, okay, so here you write the SLPP. I think writing down the SLPP is not at all a problem. I will rather do the step simplex table for this basis. So writing down the SLPP, so simplex here, it is x1 less than 1, x2 less than 1, this thing. So let me write down. So this is BV x1, x2, x3, x4, x5, and then I will have b bar. There are 3 in equation, so I will have 3 extra variables, and this is in 2 variable problem, so I will be having that only. So it will be like 1 0 1 0 0 1. And then x2, for x2 it is 1 0 1 0 1, and x1 less than equal to 2. That was an unnecessary extra constraint, but such situations can happen when you are dealing with too many equations and too many this thing. So this is an SLPP, and so like you will actually never have a chance to see the equations yourself. You are supposed to write the algorithm, and the computer would be doing that, minimizing x2. So I will write 0 1 0 0 0. So that's what it is. Now for 2 0, the point would be, for 2 0, the point is like 2 0 minus 1. So that is how it will satisfy the first row. And then this will be 1, so that x2 plus x4 equal to 1. And then x1 plus x5 is equal to 0. So that's, so then the age are basic variables are x1. No, I should put x3. Let me put x3 here, because the x3 column is already 1. And then x4 column is already 0 1 0. And then let me put x1. Okay, so this is what I am targeting. Okay, so, right now do not write this. This is my SLPP anyway. I am going to write that same table, simplex table. Write down the simplex table. So simplex table is BV x3 x4 x1 x1 x2 x3 x4 x5 b bar, and I have to transform column below x3 to that is fine. Column below x4 to 0 1 0, which is fine. And this is x1. Let me write, this is x1. Okay, this one is x4, the middle one. Yeah, and column below x1 has to be converted to E3. Therefore, what I have to do, I have to take the third row and subtract it from the first row. So that will give me 0 0 1 0 minus 1 minus 1. Rest of them are the same. One 0 0 0 1 2, and here I have to make the entries of C0 below the basic variables. So this is already 0, x2 is 1, x3 is already 0, x4 is already 0, this is 0, this is 0. So this is the simplex table. Okay, now this simplex table has a -1 actually. So the simplex table is telling us, what is the simplex table telling? Now the simplex table is telling us you are at, it telling us what? Now we are at the point x1 is equal to 2, x2 is equal to 0, x3 is equal to -1. You see the right hand side b bar column entry to the right of x3, it is -1. Huh? That is how. And then x4 is equal to 1 and x5 is equal to 0. We are at this, and at this point, at this vertex, c bar is greater than equal to 0, which basically means you are outside the feasible set. You are at a vertex like point whose affine cone over whose affine cone this minimize x2, like this is minimized. So that is why c bar is greater than equal to 0. The objective function is minimized. That is what it tells. Now then your question was, now then what do I do? What do I do next? I mean, as a computer, what is my next step as algorithm? Then the algorithm says, what you do, you pick that b bar. Here in this example, there is only one negative entry, but in general, a b bar might be having 2, 3, 4, 5 negative entries. So pick one that has the negative entry. So right now you have 1, and then turn it positive. How do you turn it positive? Now multiply by -1. So then what you do the following. I will again have to, okay, I will write it here. Turn it positive. So if you turn it positive, what you actually have, BV, x1, x2, x3, x4, x5, b bar, okay. Change it positive, okay, make it positive. So then what you will do, you will write 0, 0, you will write a -1. This is a problematic situation. And then you write a 0, you write a 1, and then you write 1, and the rest of the things you will write as such, whatever is there. So whichever column you made positive by multiplying -1, that is fine. The rest of the columns you write as such. Rest of the rows, sorry. And it was actually, because you are doing it, we are doing it for the first time, so I am writing this table. Otherwise writing this table is not necessary. Acha. So okay, fine, I turned it positive by doing this. So what is the problem? Now the problem was that earlier I used to have, because x3 was the first basic variable, earlier I used to have e1 over here, and that has changed to -e1 over here. So I have e2 now, I have e3 now, but I do not have e1, and I have to have some e1. How do I do that? Now in that row you search for some positive entries. Okay, you search for some positive entry. For example, you have a positive entry over here below x5. What will happen if you do not have any positive entry? Now look, if all these entries in this row are less than equal to 0, this means 0 times x1, 0 times x2, -1 times x3, 0 times x4, 1 times x5 equal to 1. That is what it reads. But that is also, if that is also negative or something, it will mean that some non-positive times x1, non-positive times x2, non-positive times x3, non-positive times x5, everything non-positive times, and that is finally becoming 1, which is positive. That is not possible. Okay, if somebody takes c1 times x1 plus c2 times x2, every coefficient is non-positive, less than equal to 0, and x1, x2, x5 are greater than equal to 0, and somehow this turns out to be 1, that is not possible. It cannot happen. So that is, if that is occurring, that means the set is empty. Okay, so then you say that set is empty, you don't do anything. So otherwise what will happen is that you will definitely find some positive entries in that row. Okay, so right now, for example, we have below x5, we have a positive entry in the same row. Then that is your pivotal entry. The moment you have got a pivot, you know what to do. What you have to do? This one is going out, x3 is going out, write x5 in its place. And that pivotal entry you make 1, rest of the entries in that row becomes 0. So this is 0, 1, 0, 0, 0. This was 0, but now I will make rest of the entries in that row 0. So what will that be? Now, so this is my next table. What is my next table? Now my next table, I would have actually directly got this information, this pivot, directly from here itself. Okay. But I wrote it just to explain. X3, X4, X5, B bar. So what I want now, I will keep this one x5, okay, 0, 0, -1, 0, 1, 1, because pivotal entry I want to keep 1. The next one is already 0 in that pivotal column, so I don't change that. X4, 0, 1, 0, 1, 0, 1. I don't change that also. And what about the next one? The next one was x1, and that has 1 over here. So what I do, I subtract it. So I will have x1, but I subtract the first row from the third row. So that is 1, 0, 1, 0, 0, 1. And then what do I do? Now I have to make the entry below the pivotal row, entry of C bar below the pivotal this thing 0, which is already there. So that basically means I have 0, 1, 0, 0, 0, 0. Now what has happened? So this is my next simplex table. What is this table telling me? Now I am at this is x1. Huh? My 1 and 4 are mixing. Okay. Okay. So what is it telling? Now it is telling I am at the point x for which x1 is equal to 1, x2 is non-basic 0, x3 is non-basic 0, x4 is basic 1, x5 is basic 1. That means I am actually at the point 1, 0. And at this is a vertex, this is a BFS, this is a vertex. And at this vertex, if you are looking at the affine cone, the objective function is minimized at affine cone. Now I have reached a vertex at which C bar is greater than or equal to 0. So I am done. I am at a minimal vertex. So this is how it happened that I have taken this direction to reach this one. This is how it has come. This direction we have come. Okay. So that is the step. So so what if no such choice are there? This was what I explained, that what if there is in that row there is no positive entry. That means the set is empty. Okay. Achha, those who have not noticed, after all this discussion and other things, I already have the fair written things. So you can read from there. Okay. So how did we move from there? So that part is there. Everything is there. So what is exactly dual simplex method? And dual simplex method says you first form given one basic solution that would be given to you. if I mean at one point, and you form the simplex table, and if you see this is not, I mean, and if you see that C bar is greater than equal to 0, but B bar has some negative entries, that basically means you are standing at a corner like point outside the set, such that at that point the objective function is minimized over the affine cone. In that case, you have to perform this dual simplex method. So in this dual simplex method, it says you pick one of those rows for which B bar is negative, multiply it with a -1, then you have to select. Okay, before multiplying itself, you decide on the pivot. You have to decide on the actual probably pronunciation is pivot, but I sometimes also say pivot. Okay, so before that you have to decide. I will tell in this example how exactly I am deciding. So for example, write the simplex table for the basis x3 x4. Look at this example. It says minimize this. So I want to write the simplex table for the basis x3 x4, x1 x2. This is SLPP given itself, so I don't have too much of problem over here. Okay, and I have x3 x4, and here it is for 1 1 minus 1 0 2. This is supposed to be first time I am writing 0 1 0 1 1, and this was supposed to be 2 1 0 0 0. Now I want to write the simplex table, so I have to make the column below x3 like 1 0. So then what I have to do, I have to do -1 plus 1. Okay, let me simply erase that. Okay, and -2 1 0 0 1, that is fine, and then entry is below them. So this is the simplex table. This is the simplex table for x3 x4. Fine. What is it telling? Now you are actually at the vertex or vertex like point, a corner point, -2 1. You are at this point, and at this point the affine cone, over the affine cone, the objective function is minimized because C bar is greater than equal to 0. Okay, so this is your W, and C bar greater than equal to 0, which means this means objective function is minimized over affine cone. Fine enough, but the problem is that this is outside the set. So you want to change. Now what do? Now I will multiply a -1. After multiplying the -1, there are two elements which will become positive. So I have two choices for a pivot. Which one I will take? Now look, after taking a pivot, suppose I take this first one pivot. If I take the first one pivot, then I will make this 2 0. Okay, the 2 at the bottom, that I will have to convert to 0. In that case, what I will do, I will take 2 times the first row and add it to the third row. So that will make it 0. But then look, then 2 times this particular entry will become -1 in the whole process. Okay, and I cannot, I mean, I always want to keep the C bar greater than equal to 0. So therefore, what I am going to do, I am not going to select the first one as my pivotal element, but I will choose the second one as my pivotal element. Okay. Why? Now I just found out 1 divided by 1 and 2 divided by 1, or you can say 1 divided. So whichever is smaller, what I did, now I found out the ratio 2 divided by absolute value of -1. I mean, they are now negative, so that they will become positive. And I also said this is coming from here. This one is from here, divided by this absolute value of -1, and found out the minimum. Whichever satisfied the minimum, that is what I have made my pivot. So I understand that in my next table what will happen. Now in my next table, x3 will go out and x2 will enter. BV, x2, x4, and I have x1, x2, x3, x4, and B bar. So what will happen? Now I am anyway going to multiply that by 1. Now I will multiply that by -1. 0, that is 2, no problem. And this one has to be, I mean, because that column has to be changed to 1 0 kind of a thing. So I have to add that. So -1 0 1 1 -1. That is fine. And this, the one below x2 in the C bar row, that also has to be converted to 0. So that will be 1 0 1 0 -2. Okay, so what happened over here? Now I have come to the following point. X1 is 0, x2 is 2, x3 is 0, x4 is -1. I have come to the following point. From that W, I have come to a new W, 0 2 0 -1. And here also, at the affine cone structure, like over the affine cone structure, this objective function is minimized and the value right now is like 2. Okay, but nevertheless I am still outside. So then what do? Now I do the same simplex, dual simplex step again. Now to do that, what will I do? I will have to multiply -1. That is fine, but once I do that -1, so the positive things become negative, so that E2 will change. So here only one negative entry is available, so that is my pivot. So in that case, it means in the next table, x2 is remaining. This was what? That is fine. x2 is remaining, and then x4 is going out. Instead of x4, I have x1 coming in. Fine. So after x1 comes in, what will happen? I will change this to with a minus sign. So I will change this with a minus sign. I am writing the second row first. x1, x2, x3, x4, B bar. I will write the second row first. The second row is 1 0 -1 -1 1. Then first row, now first one, I will have to make that entry 0. So it will be 0 1 0 1 1. That will be the first row. So this is the second row. That is fine. And so I have, look, the column below x1 is second variable, so is E2. The column below x2 is E1, no problem. And also I have to make the entry below x1 0, because x1 is a basic variable. So for that I will have to add it 0 0 2 1 -3. So what happens? Now the next W, the point that I am at, Next W is what? Now next W is x1 is equal to 1. I am reading from the B bar column, x1 equal to 1, x2 equal to 1, x3 non-basic, x4 non-basic. I am at this W. Okay. And what happens? Now here also C bar is greater than equal to 0. But then I am at this is a BFS. I am at a vertex only. And then I stop. Okay. This is the dual simplex step. These are the steps. When you get more than one, you will have to follow this minimum, this rule, which also have to be, this is in order to, this rule comes in order to keep the C bar greater than equal to 0. Earlier also you had that minimum ratio rule, that was in order to keep that B bar greater than equal to 0. So it was that way. Okay. Okay. So this is the answer, and here are some exercises. The complexity of the simplex algorithm. The simplex algorithm complexity is actually exponential. Complexity means worst case complexity only. So for that, Klee and Minty in 1971, they supplied one example. This is an example of a hypercube kind of a structure. Okay. And in this, they gave the problem, and here they said, okay, you have to fix some number delta between 0 and 2. For example, in our example, I took delta to be 1/3. Okay. And for n equal to 3. Okay. So then if you minimize, if you consider this problem, and you start with the BFS 0, 0, 0. So what it does is it goes through all the 2 power n minus 1 vertices. So that it basically means before giving you the optimal result, it has to perform 2 power n minus 1. You forget that minus 1, about 2 power n iterations. I mean, n equal to 100, it will never give you the answer. Okay. I mean, it will give, but after ages. So that's how it is. So for example, I have given the illustration. The problem would look like this only. Okay, for n equal to 3 and delta equal to 1/3, the delta, whatever delta you want to take between 0 and a half. So I have taken 1/3. The problem would look like this only. Okay, so x1, x2, x3, because you have 3 variables, and then you will have 5 extra variables, because it will start from I equal to 2 to n. So that is how x1 is less than equal to 1, and then you have 2 and 3, so therefore you have 4 equations from there, 4 equations from there. So you change this and you try this, you will be seeing this. So knowing that, so theoretically exponential, but what happens, people, those who have observed it, they report that, those who like employ this, they report that in on an average it takes about n cube kind of operations. So it is quite fast. People don't give any, these are, what do I say, people, the report, it works quite fast. That is how, no theoretical justification. You cannot. Acha, this is the sensitivity analysis, the old days. Nowadays, nobody does that, but still I will tell you. The story is like this. Some industry approaches to you, gives a big, like some 100 equations, some 50 variables, maybe, or 60 variables, okay, and gives one LPP saying that I need solutions to this, or something like that. Suppose you are working in with that industry itself, so you do the computations. The computations took maybe some 3-4 days with whatever computer you have, and then finally you found the optimum table. Okay, this is the one for which it is minimum. Fine. And then the next day, because of some extra information the company gets or something, the company says, oh, there was an error. Instead of in the constant column, actually that B, I mean, normally it is minimize something x equal to b, that kind of a thing, or x less than equal to b, in whatever way the company has given you the matrix and vectors, whatever it has given. Oh, sorry, that constant column, there are some changes. Instead of b, it will change to b dax. Now what do? Do you want to again run the program for 3 extra days, and with like again you want to do that, or there are something else, whether you can start from the final table, the optimum table, that kind of a question? Or the company comes and says, oh no, last time we computed this cost vector, but this time things have changed, the variables, I mean many other things have come out, and then now cost vector is this one. This one I want to, the objective function, this is the objective function I want to minimize. I don't want to minimize that one. So what do? Or the company may say that, okay, last time I considered these 5 variables. These were my 5 variables. This time I have introduced one more variables that also has to be considered. So accordingly, that means they are adding one more column to the A matrix. That is also a thing. So whether you can continue somehow from the optimal table, that's the idea. Nobody guarantees what you are doing. I mean, in some of the cases it is okay, but otherwise, I mean, nothing is beneficial as such guaranteed. But normally people advise, those who do the practical thing, they advise you to do these modifications, whatever I am going to say, and start from the optimal table. That's what, and they say that it saves the time. Okay, for example, so we have our problem over here, that is problem given. The initial table, that is the problem table, I have written over here, and the optimal table I have written over here. Okay, so for example, the company says that I want to add a new variable. Okay, that basically means company is going to add one more column. Okay, so for example, this one, it has added, where from this column 1 minus 1 1 I have added. Well, the C bar entry, okay, the C bar entry below this thing was, if you look at the problem, in the problem we were trying to minimize minus 2x1 minus 4x2 minus 3x3. Okay, these things are written, and then the company now also wants to minimize the same thing plus y, and by adding one more column. So that is one more column. This 1 minus 1 column, that is given by the company. I am not doing anything. Assume that is the case. Now what do I do? Question is that. Fine. So now understand, your optimal table is not visible over here. Let me look at, let me write the optimal table over here, huh? So that you can see. X5 B bar 2, so this is X2 X4 2 1 1 0 1, and then minus 1 0 2 1 minus 1 1, and then 6 0 1 0 4 12. Okay, that was my optimal table for the old problem. Now the company changed the problem. But what do I realize? Look, earlier x2 x4 was basic variable, optimal basic variable. Now also if I take x2 x4, what will happen? Now if I take x2 x4 and try to compute the simplex table now also, I will get the same matrix. I will have the same thing. Because earlier this part of the matrix was the same only. I mean this matrix 1 1 3 1 0 2 1 1 0 1, it is present now also. Okay, it was earlier, now also it is present. Choosing x2 x4 as basic variable means what? Now I formed the basis matrix multiplied by B inverse. So if I also multiply right now also the same thing, I should be getting the same this thing. Okay, so then I understand if I choose that same basic variable x2 x3 x4 x5 and B bar, I will get the same matrix. Oh, sorry, not just B bar now. I will have to write Y and then B bar. So if I write x2 x4, then I understand these entries. Either you form the simplex table at x2 x4 for this SLPP directly. That means you just multiply by B bar. So you will be doing some little extra computation, but that is not much. You can do directly. So it is basically form the simplex table at the optimal, the old optimal basis. So that's what I am trying to do. And I understand what will come. Now it will come this way: 2 1 1 0 1 minus 1 0 2 1 minus 1. B will come. B, what was the other entry? I forgot to copy. 3 1. Huh? This was 3. B will come the same B way only. So 3 1. Okay. So earlier what was the C bar? Now earlier I had taken some multiples of row added to this, and I had got everything. I had got it to what place? Now I had got it to 60104 by taking certain some whatever multiples. Okay, remember, if I imagine earlier Y was also present, but corresponding column was all zeros, C bar entry was all 0, then they would have remained the same. Okay, so I can put a 1 right now. I want to minimize that. Right now I want to minimize, so I keep a 1. This I have to convert to 0. But what is the column corresponding to this? Now, oh, acha, you want to get the column corresponding to this Y, na? What have you done? Now I have multiplied it by B inverse. Now what was your B? Now B was x2 x4. So what was the basic matrix? This was 12. Anyway, what was your basis matrix? Now basis matrix was B for x2 it was 1 1, x4 is 1 0. Then what is B inverse? Now B inverse you compute. What is B inverse? Now B inverse would be like what is that? 0 1 1 minus 1. I think that should do 1 0 1 0 and then 1. B inverse is that only. Okay, this is your B inverse. Now B inverse. So then the entry that you will get below Y must be this only, na? B inverse multiplied by 1 minus 1. That is what it would get converted, because that is what you have multiplied. Okay, so that means 0 1 times this, so that will be minus 1, and then 1 minus 1 times this, that would be 2. Acha, so this one would be minus 1 and 2. Okay, that column I fixed. But what about this particular entry 1 that is supposed to be 0? We'll make that 0. How do I make that 0? Now, I don't know. You add the first row to this one. That will make that entry 0. Okay, but that will be a problem, na? What will be problem? Na, see, no, that, let me see. Is that fine? Oh, sorry. What am I saying? Why should I make the entry below y0? I have the optimal basis itself. Okay, that's my optimal basis. And what else am I supposed to do from here? So I took the old optimal basis, computed the table at this place. Okay, fine.
So we must find the last entry of C bar, right?
A last entry of C bar. Ha. Right. Array. Sorry. Thank you. I forgot what to do. So I have to convert this to last entry of C bar. So how will that come? Now this will come from taking that entry minus that CB B inverse, that particular this B inverse that I have found. And what is that CB? Now CB was to be taken from X2 and X4. So X2 and X4 CB transpose, so minus 4 0. So this is X2 and X4 from there, and this have to be multiplied by minus 1 2. This is the CBB inverse, that entry. This difference, so that is the next difference. So what is that? This is 1 minus 4, so that gives me minus 3. So for the simplex table, if I want to convert the simplex table, this one will not be there. Instead of it, I have minus 3 over here. So what happened? Now I formed the simplex table at the old optimal basis and found what? Now, acha, C bar has a negative entry. Well, if C bar has a negative entry, then you know how to proceed with the simplex table. So proceed. I apply the simplex method and proceed. So accordingly proceed. So that is one step that you do. Is that okay? Here I have done it. So whatever I am doing there, I have also done it. So in case you do not, you forget, this is how you start. Acha, what about this one? Now the company gives you B dash instead of B, the constant vector. Now what actually has happened in the old optimal table? What has it done? Now it has computed B inverse B. Well, in that case, if the company has given you B dash, then you will have to compute B inverse B dash. And if that B inverse B dash turns out to be greater than equal to 0, since you are at an old optimal basis, so you will say the new optimal basis is fine also. Like whatever the old optimal basis, it also works out to be optimal for the changed problem. If B inverse B dash turns out to be greater than equal to 0. But somehow if B inverse B dash, that is the right side vector, turns out to have some 1 or 2 negative entries, then what do? Now apply dual simplex step, the one that we discussed earlier. Okay. What about changing C to C dash? Now, there you have to compute C dash transpose, the the bar of C dash transpose start like fresh. So that row has to be computed fresh from the old optimal table itself. So you start with the old optimal table, just write CDAX, assume that you are going to change CDAX to CDAX bar. You change CDAX to CDAX bar. If it turns out to be greater than equal to 0, you are happy, you are at the minimum. If it has some negative entries, proceed with simplex method. Okay, so that part also we know. The only thing that may happen that you are adding a new constraint, some new constraint is being added. Okay, what do you do then? That also can be managed. It is not that it is difficult. So for example, in the previous problem, there were only two problems. I mean two constraints, this one and this one. The first two were there. Now you have added a new constraint. Imagine if I am adding a new constraint, that means I am going to add one more variable. Okay, that is what I am going to do. Now here is a small observation. If you are adding a new constraint, what is happening to the feasible set? Now see, earlier you had this size of a feasible set, whatever is the size of the feasible set. Now you have added one more constraint. That means you are going to get a subset of that only. Okay, it's a smaller one, a subset of the old feasible set. You are going to get the more constraints, the smaller set, because the smaller number of points will satisfy more and more constraints. So that's how you will get smaller subset. Now what you do, whatever was your old optimal solution, just check whether that solution satisfies the new constraints or not. If it satisfies the new constraint, well, it was minimum over a bigger set. Now you are only talking about a subset, and if that point is available here, this is bound to be the minimum. Okay, you had a bigger set and you have found a point which is minimum, and then you are taking a subset, and this subset also contains that point, minimum point. Then in that case, that point will be minimum over this subset. Of course it will be. That was minimum over the bigger set, over the superset itself. So first you check whether it satisfies it or not. If it satisfies, then the old optimal solution is the new optimal solution. There you don't have any problem. If it does not, then what has happened is that actually this new constraint is actually this is going to draw a hyperplane kind of a thing, which is keeping your old optimal point outside. Now it is going to make it like a corner like point. Remember, so this is a hyperplane kind of a thing which will separate out your old optimal point. I mean, it will chop the old feasible solution set into two parts. In one part it will have the new feasible set, and the other part will remain outside, and which contains the old optimal solution also. So if you start with the old optimal basis, BFS, whatever old optimal solution, what you will get, the simplex table, if you are going to compute, in that simplex table you are going to get a B bar entry negative. In fact, you will get it for this particular the new inequation. You are going to get it because of this, because this one is keeping that separating, I mean throwing it out. Actually it is keeping that out. So you do that and then you apply dual simplex method. Okay, so that is the whole idea over here. This is what it is. For the, so first you have to write down the constraint. This, remember the new constraint was x1, x2, x3 less than equal to 2. What you do, like this is like here, x1, x2, x3, and then this is a new variable that you are adding. This is equal to 2, no problem. But you have to remember this x2, x4, they were earlier like they were 1, 0. X2 was giving 1, 0. X4 was giving 0, 1. So fine, I have kept as such. Now this is 0, 0, 1. So I will have to change what now this particular 1 to 0. This 0 is already 0. I don't have a problem. This is 0, 0, 1. I do not have a problem. Okay. This entry is anyway 0. I do not have a problem. The only thing that I am going to change is this entry. I have to make 0. So in the process, what happens? This particular entry becomes negative. Okay. This becomes negative, and it is bound to be negative because the old optimal solution was not satisfying that new inequality. And from here, how do you proceed? Now you proceed by dual simplex method. Okay, this is why dual simplex method was told to you. Questions?
Excuse me, sir.
Huh?
I might have missed this when you explained it before, but do we necessarily know that the dual simplex method will terminate? Like, for example, if B has a negative
yes,
entry and
yes,
we subtract it,
and then you get 2 negative entries,
yes,
maybe
sir.
5 negative entries.
Like,
yes,
sir.
Actually, what happens? If you, I did not spend time over there, but here is this. See what happens if we are careful. Okay, there are finitely many basic solutions. Okay, there are finitely many basic solutions. The algorithm must terminate if cycling is avoided. We are only talking about, see, how many vertices are there? Finitely many. So even if it is the degenerate case, how many ways you can get the same vertex? I mean, how many different basic solutions? I mean, you can get how many different bases can correspond to it. That is also finitely many. Okay, so because there are finitely many basic solutions, the algorithm must terminate if you are able to avoid cycling. Actually, people apply the Bland's rule kind of technique over here also, but if, like, that was not, those who are interested, they can read about it. Cycling can be avoided.
Okay, so it's basically a similar argument as for the primal simplex method.
Exactly.
You just said that there are finitely many BFS.
True. Actually, if you are that interested, what I would request you, you take a problem. So where you have, for example, this table, and write the primal and write the dual, and see how they are changing. I mean, what are the things? You will see that this primal problem being solved by primal simplex method, dual problem is getting solved by dual simplex method. They are going, like, there is a whole lot of relation. Okay, so but since my target is not that, actually dual simplex step is just given to tell you that this is how you start. I mean,
yes,
proceed.
sir, but it was apparent because, like, in the dual problem, what we do is we look at what are the possible upper bounds for that, and we find the lowest upper bound. So here also we're doing that sort of thing, right? We're looking at vertices that are not feasible, but they give you the lower bounds rather for that thing, and then you climb the lower bounds to get the greatest lower bound.
True. That is how. Yeah. And that finishes my discussion, our discussion on the simplex thing. Okay, so from next class onwards, I will be talking about transportation problems. That is tomorrow. Okay, and then some exercises are, as usual, exercises are there. Okay, and I think some 20 odd answer scripts are remaining. So once I evaluate that, maybe in a day or two, I should be sending you the answer script. Or that will take time. I will have to email one by one. But yeah, that is what we are going to do. Those again, I am emphasizing those who are worried for exam. I am making myself very clear. Okay. This time I think I am going to give you 2 hours because you said you do not have enough time. But please do not copy. It is very easy for me to find out if you are copying. So please do not do that. It's not a good thing. You have enough time, and I am asking questions directly based on your understanding. What is this? What is that? Draw this table, draw this figure. That is what I am asking. Few questions from exercises for which you have enough time to solve. You solve, you discuss among yourself, make your solutions ready to all these exercises. You do hard work, you take away mark. I am not holding you back. I mean, if you do hard work, that is what I want. You study, you get everything ready. But at exam, you do not cheat. And then there will be one, maybe 1 or 2. I mean, there will be one, maybe some new question where, which is like, which will be challenging, a little bit challenging. Okay, that's what it is. So it is very clear. You spend time, you get mark. So, but do not copy, huh? Okay, so these are exercises. I stop here.